I think you've been exposed to the idea of a function at some point in your mathematical career. But what I want to do in this video is explain it a little bit more formally than you might be used to, and then relate it to some of the concepts of vectors and linear algebra that we've seen so far. So a function literally is, so I'll write it like this. A function really is just a relation between the members of one set and the members of the other set. So let's say I have some set x. And for every set x, I'm going to relate or associate, for every member of that set x, I'm going to relate that member to, or associate that member with another member of a set y. So if I imagine that that is my set x, and that this is my set y, right there, and y doesn't have to be smaller. That's just the way I drew it. The function is just a relation that if I just take a member of my set x, so if I just take a member of it, let's say that's the member that I'm taking it, we're visualizing as a point. This function will say, OK, you gave me a member of x, then I will give you a member of y associated with that member of x. So the function will say, you give me that, then I will map it. I will map it to that member right there. I'll use the word map it. And that really just means relating it to or associating with another member of y. And if you give me some other point right here, I'll relate it to another member of y. I'll relate it to another member of y right there. I might even relate it to the same member of y. And so this notation just says this is a mapping from one set x, and I'm speaking in very general terms, to another set y. And so you're probably saying, hey, Sal, this is very abstract. How does this relate to the functions that I've seen in the past? Well, let me just write down a function you've probably seen a lot in the past. You've seen people write, or you've dealt with f of x is equal to x squared. How would we write this in this notation? Well, this is a function, assuming that it's kind of the traditional way that you see it. This function, and actually let me just write it with the f. I was going to write it with the g of x, just so that this doesn't always have to be an f, but I think you get that idea. In this case, f is a mapping from real numbers, right? The real numbers are everything that I can put in here. And actually, this is part of the function definition. I could constrain this to just be integers, or just be even numbers, or just be even integers. But this is part of the function definition. I'm defining the function to be a mapping from real numbers. I'm saying you can put any real number here, and it's going to map. It's going to map to, well, it's going to map to real numbers. So in this case, if x is real numbers, it's going to map to itself, which is completely legitimate. So if this is the real numbers, and obviously the real numbers would go off in every direction forever, but if this is the real numbers, this function mapping is just taking every point with f and mapping it to another point, or every point in R and mapping it to another point in R. It's taking every point and associating with it its perfect square. And I want to make a very subtle notation, or at least in my mind, the first time that I got exposed to functions, I was thinking, you give me an x and I square it, and I'm giving you the square of x. And that's true. You are doing that. But at least the way my brain worked, I kind of thought of it as I was changing my x into another number. And you can maybe view it that way, and that might actually be the best way to view it. But the mathematical definition I'm introducing here is more that I'm associating x. I'm associating x with x squared. And this is actually another way, this is another function notation of writing this exact same thing. These two statements right here, this statement and this statement, are identical. This statement you've probably never seen before, but I kind of like it because it kind of shows the mapping or the association more. While this association, I kind of think that, look, you're putting an x into a little meat grinder or some machine that's going to ground up the x or square the x or do whatever it needs to do to the x. This notation to me implies the actual mapping. You give me an x, and then I'm going to associate another number in real numbers called x squared. So it's going to be just another point. And just as a little bit of terminology, and I think you've seen this terminology before, the set that you are mapping from is called the domain. And it's part of the function definition. I, as the function creator, have to tell you that, look, every valid input here has to be a set of real numbers. Now, the set that I'm mapping to, This is called the codomain. Codomain, which is, and I guess the obvious question that you're probably asking is, hey Sal, when I learned all of this function stuff in Algebra 2 or whenever you first learned it, you're like, where did, we never use this codomain word, and actually I don't think it has a hyphen in it, but we never use that codomain word. We have this idea of range. I learned the word range when I was in 9th or 10th grade. How does this codomain relate to range? And it's a very subtle notation. So the codomain is a set that you're mapping to. In this example, this is the codomain. Codomain. In this example, the real numbers are the domain and the codomain. So the question is, how does the range relate to this? So the codomain is the set that can be possibly mapped to. You're not necessarily mapping to every point in the codomain. I'm just saying that this function is generally mapping from members of this set to that set. The range is the subset. Let me write it this way. It could be equal to the codomain. It's some subset. A set is a subset of itself. Every member of a set is also a member of itself. So it's a subset of itself. So range is a subset of the codomain. I keep adding a hyphen there, or dash. Is a subset of the codomain which the function actually maps to. That the function actually maps to. Actually maps to. Maps to. So let me give you an example. Let's say I define the function. Let's say I define the function g. And it is a mapping from the set of real numbers. Well, let me say it's a mapping from R2 to R. So I'm essentially taking two tuples and I'm mapping it to R, and I define g. I'll write it a couple of different ways. I could write, so now I'm going to take g of, let's say, two values. So I could say xy, or I could say x1, x2. Let me do it that way. G of x1, x2 is equal to, well, let's say it's always equal to 2. It just always equals to 2. It's a mapping from R2 to R, but this just always equals 2. So what is our, and let me write it the other notation, just because you probably haven't seen this much. But I could write g of g maps any points x1 and x2 to the point 2. This makes the mapping a little bit clearer. But just to get the notation right, what is our domain? What is our domain? What's the real numbers? That was part of my function definition. I said we're mapping from R2. So my domain is R2. And I should actually make that with that little line there. Now what is my codomain? My codomain. Well, my codomain is the set that I am potentially mapping to, and it's part of the function definition. This, by definition, is the codomain. So my codomain is R. Now, what is the range of my function? What is the range? The range is the set of values that the function actually maps to. In this case, we always map to the value 2. So the range is actually just the value 2. And if we were to visualize this, R2 is actually, I wouldn't draw it as a blurb. I would draw it as the entire Cartesian space. But I'm just giving you kind of an abstract notion. That's R2. If I really had to draw R, I would draw it as some type of a number line. Actually, let me do it that way, just for fun. You don't normally see it written that way. But I could just draw R like that's R2. And I could just draw R as some straight line. So this is the set R. I could draw it like that as well. But let's just say it's a set R. And my function g essentially maps any point over here to exactly the point 2. Right? 2 is just one little point in R. And my function g takes any point in R2, any coordinate, x, this is some point, this could be the point 3 minus 5, whatever it is. And it always maps it to the point 2 in R. So if I take that point, it maps it to the point 2. That's what g always does. So G's codomain, you could say it's all of the real numbers, but its range is really just 2. Now, if I write the example, if I say that Let me do another example that might be interesting. If I just write h is a function that goes from, let's just say it goes from R2 to R3. And I'll be a little careful here. Goes from R2 to R3. And I'll write here that h of x1, x2 is equal to, so now I'm going to a higher dimension space. So I'm going to say that that is going to be equal to, let's say my first coordinate, I could say in R3, or my first component at R3 is x1 plus x2. Let's say my second coordinate is x2 minus x1. And let's say my third coordinate is x2 times x1. Now, what is my domain and my range and my codomain? So my domain by definition is this right there. My codomain by definition is R3. And notice I'm going from a space that has 2 dimensions to a space that has 3 dimensions, or 3 components. But I can always associate some point with an x1, x2 with some point in my R3 there. And now a slightly trickier question here is, what is the range? Can I always associate every point? Maybe this wasn't the best example because it's not simple enough. But can I associate every point in R3? Can every point in R3, so this is my codomain. My domain was R2. Now, and my function goes from R2 to R3, so that's h. And so my range, as you could see, it's not like every coordinate you can express as in this way in some way. Let me give you an example. For example, clearly the term, I could put some x1s and x2s here and figure it out. Let's do that. Let's take our h of, and let me use my other notation. Let's say that I said h, and I wanted to find the mapping from the point in R2, let's say the point 2, 3. And then my function tells me that this will map to the point in R3. This will map to, I add the 2 terms, so 2 plus 3, so it's 5. I find the difference between x2 and x1, so 3 minus 2 is 1. And then I multiply the 2, 6. So clearly, this will be in the range. This is a member of the range. I shouldn't write like that. I should write it like this. The member of the range. So for example, the point 2, 3, which might be right there, will be mapped to the 3-dimensional point. It's kind of just drawn as a 2-dimensional blurb right there, but I think you get the idea. It would be mapped to the 3-dimensional point 5, 1, 6. So this is definitely a member of the range. Now, my question to you, if I have some point in R3, let's say I have the point, I'm doing a different color. Let me say I have the point there. Let's say that this is the point. Let's say this is the point 5, 1, 5, 1, 0. 5, 1, 0. Is this point a member of the range? It's definitely a member of the codomain. It's in R3. It's definitely in here, and this by definition is the codomain. But is this in our range? Well, if I take, 5 has to be the sum of 2 numbers. The 1 has to be the difference of 2 numbers. And then the 0 would have to be the product of 2 numbers. And clearly we know if 5 is the sum and 1 is the difference, we're dealing with 2 and 3. And there's no way that you can get the product of those numbers to be equal to 0. So this guy is not in the range. So the range would be the subset of all of these points in R3. So there'd be a ton of points that aren't in the range. And there'll be a smaller subset of R3 that is in the range. Now I want to introduce you to one more piece of terminology when it comes to functions. These functions up here, this function that mapped from points in R2 to R, so its codomain was R. This function up here that is probably the most common function you see in mathematics. This is also mapping to R. These functions that map to R are called scalar value or real value, depending on how you want to think about it. But if they map to kind of a one-dimensional space, we call them a scalar valued function or a real valued function. So scalar valued or maybe we could call it a real valued function, which is pretty much all of the functions that you've probably dealt with up to this point in your mathematical career, unless you've kind of taken some vector calculus or whatever not. Now, the functions that map to spaces or subspaces that have more than one dimension. So if you map to R or any subset of R, you have a real valued function or a scalar valued function. If you map to, Rn, where n is greater than 1, so if you map to R2, R3, R4, R100, you're then dealing with a vector valued function. So this last function that I define over here, h is a vector valued function. Anyway, I think you now have at least the mathematical notational tools to understand what I'm going to do in the rest of this playlist. And hopefully you found this reasonably useful.